Well, hello everyone. This is the second section in chapter 9. It's a very short section, very visual, deals with what are called direction fields. Essentially what a direction field is a way to visualize a differential equation, a first order differential equation. So I'll give you an example. If you had a differential equation, a very simple one like that, and you wanted to kind of visualize what did it look like? Well, essentially what this is saying is that the slope of the function y is equal to the x plus y coordinate. And if you were going to do it by hand, it would be extremely laborious, and I'm not going to even attempt to do it by hand, really. But just to take you through what the process might look like roughly, is that you take a point like the origin. Now, it's 0, 0. So the derivative at this point would be 0. So imagine a horizontal line. To represent at that point, the function would be a horizontal function. Next, you might take a point like 1, 1, which is here, and 1, 2, 1, 0 is here, and 0, 1. So let's look at what these three would be. At 1, 0, the slope would be 1, so that would be about here. At 1, 1, it'd be a bit steeper, it would be 2. At 0, 1, it would be the same as that one, it would be 1. And then if you, let's say you went down this way, you went there. Well, that point there is negative 1, 0, so that would have a slope be negative 1. This one here would be 1, negative 1, so that'd be a slope of 0. If I continue to do all the other possible coordinates in this very small selection, kind of setting up here, you can imagine that at each one of these points, there'd be an x and y coordinate, and then we could add the x and y coordinate, and that would eventually give us the slope of the curve at that point. For instance, this guy here is 2, 2, would be a slope of 4, and this one would have a slope of 3, and this one would have a slope of 2, and a slope of 1, and then 0, and this one would go to 1 there, be even steeper. That one there, then you'd go negative a bit, it'll be even more negative, even more positive, and so on and so forth. When you are finished, you would have what is called the direction field. So I'm just going to try and very, very roughly imagine what this would look like. So when I draw a line like this, the slope of that line represents what the slope would be at 2, 2. So I could tell you that the slope of that line was 4. If I do this one, it's horizontal again, and it goes down the way. Let's check that. Oh, no, it isn't. Negative 1, negative 1. That's even more steep, and that's even more steep. That would be that. Then it would be horizontal. Then it would be a little bit positive. And what this be? Negative 2, negative 1, 0, steeper and steeper. Yeah. So maybe not a perfect match, but that's roughly how a direction field is created. You can see that it's very cumbersome, time consuming, so we're going to let software do it, thankfully. But let's show you one more thing you can do. If someone says to you that y of 0 equals, oh, let's say 1. Now we know that means when x is 0, y is 1, which is just another way of saying the coordinate 0, 1. So if I found the coordinate 0, 1, it's here. What you can do is you can imagine that this continues and then it meets up with that one going this way. And then it comes here, what's that one there? And it goes to this one, right? So it goes like that, and then it points here, and then it points down that way. So you can see that what you end up with is basically the shape of the function y at that particular solution. Two things I want to show you now. First one is, I want to show you a much easier way of doing that guy, i.e. the direction field, also called various other names. The direction field's the one we're going to use. It's the one that is used in WebAssign. So bear with me for a few moments while I set things up. Let's go to Canvas and see the software that's going to do that job for us. And we go check. It's hard for me to see what you should see, so I hope you're seeing it, yes. So, let's go home and find it. Should be in here. No. And what's wrong here? Oh, here we are. And just hide those and make that go away. So what we have here is our derivative dy by dx. Here, you type in the function that you want. In the example I just did, I chose a pretty simple one, x add 1. So when I yeah, there we go. So when I click off that, we have got the guy. And you can zoom out, or more interestingly, you can zoom in. Here is the point. If you imagine this point, go along, goes down, swings over, swings round, swings up, it looks like it could be a circle. If I go here, and I change this now to x add y, which is what I thought I'd done the first time. There we are. You see how much more. Let's go this way. Now, can you imagine it would hit this one, then it would go something like this, and it curves up. Basically, that's how you get your direction field. Now, second thing I want to show you is what the homework questions look like. There are not many of them. Let's see what they look like. So again, I'll do a doubles check because I don't have the backup of people nodding at me and telling me that we're on it. So I'm assuming we are on the homework question. So dy by dx is equal to all of this. And this is what it looks like. So we don't need to worry about that part. And they said, okay, if y of 0 equals 0, which one of these would be the curve you've got? So you imagine you're here. It's a horizontal line, so you go a little bit, and then it kinks up, and then it kinks up, and then it kind of levels off there. And then on the other side, it's very symmetric. It kind of goes like that. Think of this like a river current. And if you dropped a little paper boat there, how would it float in the current? Well, it would float something like this. And where would it go if the current went that way? It would go this way. So it looks like a big flat U. And the big flat U would be that one. Oh, of course, I've got the answers on the thing, but you can see these answers off. Oh, so far so good, right? Now, if you are told y of 0 equals 0.5, well, I know these are, the background is the same direction field, so I can pretty much just use any one of them and then we can see which picture it works with. 0.5 is here. Now I'm looking at 0.5, and to me that's pretty much virtually a straight line. So that's the guy you would pick. Now y of 0 equals 0.9. Well, if I pick this one just to say it, 0.9 is about here. If it's 0.9, do you see it kind of has a curve that goes like this? Looks like a big hat. So I would have picked this picture here. And 1.8 and so on. So I'll let you figure out the rest of those guys. Now, then goes on and it asks you from the direction field, find any equilibrium solutions. Now, equilibrium solutions are essentially places where when the, for a better word, when the curve hits the thing at 0. Well, do you see that? Although it might not look perfectly horizontal, it is meant to be. So y equals 0.5 and y equals 1.5. I'll just show you those. So the two places, 0.5 and 1.5. You see how that works? Equilibrium solutions are solutions that once the curve hits it, it stays on that line. It never really diverges, it goes horizontal. Think of it as like a population reaching its optimum level and not changing once it reaches that. Now, in the next group of questions, it's really just a matter of going back to the software that I talked to you about. Do y by x is 2 minus y. Looking at their picture and then saying which of these guys it would fit with. So I'm just going to take a note of a couple of these equations and we'll try out the software. So the first one was y equals y dashed, which is the derivative, equals 2 minus y. And another one, would be, okay, make it question 3 then. Y dashed is x, 2 take away y. I'm going to close this window. Close that one. Right, so what we want to do is we want to take this guy and type in 2 minus y. And that's it. Look for a picture that looks like that. If you want x 2 minus y, go like that. Yeah. You can look at this particular solution and actually figure out some of its features without even using software. This one we've just done is for x 2 minus y. And what the easiest thing to visualize is when derivatives are horizontal, when they are 0, because horizontal 0 matches perfectly. Now, when I look at that, do you see when the y coordinate is 2, aren't you going to get zeros? Can you see that horizontal black line at y equals 2? See how that matches? So if you went through all the pictures that they give you a choice of, you might only get 1 or 2. You'll definitely get 1, but you may get 2 that had that property. Now, there is another place, isn't there, where the value would be 2. Wouldn't that be at x equals 2? So I'm trying to find x equals 2 here. Well, that isn't telling the truth, because that should be horizontal. oh, x equals 0. Sorry, what am I talking about? X equals 0, in which case it is perfect. Can you see it? Horizontal at all the places where the x coordinate is 2. So that's essentially how you would do it. If I go back to the one that just came before that, just to take away that one. Can you see here, there's only going to be one particular situation where I know the derivative is going to be 0, and that's going to be at y equals 2, and that matches this one here. So if we think about that as a way you can kind of verify what the picture that you got from Desmos is saying, everything should, match. If you see a horizontal line where there should be one, you know you're in the right place. Okay. So far, so good. Now, that's pretty much what what these questions are like. The later question, apart from the one I'm looking at right now, is question 6, but question 5 gives you a differential equation that looks like that. And they ask you to sketch that. Well, you're not physically going to sketch it. You have a choice of 4 pictures and you pick one. And then in those pictures, there are going to be 3 sketch solutions. All they're doing here is they randomly pick, a couple of points, and they draw the curve that would go through each of the 3 points. Once you know what the direction field looks like, you should be able to figure out which one is the right picture after that. Question 6 is watch a video, so I won't waste that for you, and so is question 7. So that's a really quick section, and that's essentially all you need to know as far as directions fields go. Think of them as a visual way of representing a first order simple differential equation, and that we have a program in Desmos that allows us to sketch them, and that if someone tells you a piece of information, they're actually called boundary conditions, like y of 0 equals 1, you can draw a curve through. And that is us. Thank you.